In this video, we're going to talk about how do you use ratio tests to find out if a power series is convergent or not. It will also find the radius of convergence and the interval of convergence at one shot. First, let's remind ourselves what does it mean for a power series to converge. We want the limit when big N goes to infinity of the summation exists. So the ratio test requires all of the constants for these terms to be non-zeros. And we want to set the limit when small n goes to infinity of the n plus 1th term of this sequence divided by the nth term of the sequence to be L. And if L is less than 1, this means the next term is less than the term that you're looking at. If this is the case, the series converges absolutely. If, on the contrary, L is bigger than 1, that means the next term compared to your current term, it is going to be bigger. Then, of course, when you are adding the bigger terms, the series, when you sum this up, it will diverge. And if it's equal to 1, then we have to do further tests to see on the boundary point whether it's converged or not. Let's see an example. How do we actually perform ratio test? So in this case, we have a power series, which A is equal to 3. It means that it's centered at 3. And Cn is 1 over 2 to the n times n. So according to our formula, we have L equals to x minus 3 times the limit when n goes to infinity of Cn plus 1, which is 1 over 2n plus 1 times n plus 1, divided by Cn, which is 2 to the n times n, all in absolute value. So if we further simplify this fraction a little bit, we should get the limit when small n goes to infinity of n on the top, 2 times n plus 1 in the bottom. So this is because we have a 2 to the power of n on both the top and the bottom, so this get canceled out. And we have a 2 left in the position of a denominator, also this n plus 1. So this n gets flipped up when you divide this fraction, and this becomes your numerator. So let's further take the small n goes to infinity. This fraction should tend to 1/2. So we should have 1/2 times x minus 3 in absolute value. So here, remember the ratio test, we will have three different cases. When x is less than 1, this gives us 1/2 times x minus 3, less than 1. So we have x minus 3 in absolute value is less than 2, and this is 1 is less than x, and it's less than 5. So inside of this interval, the series converges absolutely. So in the second case, we will have L is greater than 1. This means that the next term is bigger than the current term. And if we have this case, the power series would diverge. So this means our L value is greater than 1. So x minus 3 is greater than 2. So we should have x is either less than 1 or x is greater than 5. So in this region, which you can see that is almost the complement set of this convergence interval, except for on the boundary point when L is equal to 1. So when L is equal to 1, if you solve for this equation, you should get x equal to 1 or x equal to 5. So when x is equal to 1, we have to plug back into this power series. So we should get the summation when small n goes from 1 to infinity of 1 minus 3 to the power of n divided by 2 to the power of n times n. And this is the summation when n goes from 1 to infinity of -1 to the power of n divided by n. And if you're familiar with this, this is alternating from positive to negative. So we can use the alternating series test and to prove that this is actually a convergent series. So this means that at the point when x equal to 1, this series converge. And the other one, when x is equal to 5, the other boundary point, we would also plug into the original power series we have right here. And this gives me 5 minus 3 to the power of n divided by 2 to the power of n times n, which is just 1 over n. So for this is called a harmonic series. So we can use an integral test to see what is, if this series converges. And if you take the integral from 1 to infinity of 1 over n, we know that this gives you a divergence result. So to conclude, after performing the ratio test to this power series, we first find out there are 3 different cases. Inside of this interval, it converges absolutely. And if we're in this 2 intervals, the series diverges. And if we are at the point when x is equal to 1, the series also converges. So to put it together, so the interval of convergence in this case would be from 1 to 5. 1 is included, 5 is not. And the radius of convergence in this case would be 2. So this is because if we're looking at the center of this series, so the center is at 3, and we are 2 distant apart from 3. So from 1 to 5, 1 is 2 units apart from 3 to the left, and 5 is 2 units away from 3 to the right. So r of c, radius of c, is 2 in this case. So as you can see that the ratio test, after we perform a certain series, it will find its interval of convergence, the radius of convergence at one shot.